Hello everyone, I am going to discuss with you the work of one of my MTech student which was done on the vibration analysis of foundations subjected to pulse excitations having negative phase. So, this is what is going to be the outline of my presentation. First, we will have some introduction, then I will share with you that how we modeled the problem and analyzed it. Then I will share with you some of the results and discussion, and finally the summary and concluding remarks. So, let us come to first the introduction part. We know that in the industrial structures, most of the time we have many foundations which support the various types of machines. Now, in the event of such extraordinary situation like blast or mining activity in the vicinity, this kind of situation may arrive, and here is an example when the blast happened in Bhilai steel plant due to an explosion in blast furnace, and this event took place on June 12, 2014. So, you can see that what is going to be the situation. Similarly, one accident took place on November 1st, 2017 in a power station in Uchahar, which is NTPC setup in UP, and you can see that what is the situation as shown in this particular picture. So, as I was mentioning that in case if you have industrial buildings, there may be different types of machines which are already functioning, and on top of that, let us say if such extraordinary event takes place, then along with the unbalanced force which is acting on that machine foundation, some force related to this blast or the mining activity will also occur. Now, the question is how to account for the situation if such events happen. So, in that case, we have to go ahead with the combined response of these different types of loadings. First will be the unbalanced force of the machine foundation, and second will be the force which will be applied because of such blast loading. So, to keep in mind, we took an example of hammer foundation which is shown in this particular figure, and you can see that how the machine is mounted on this foundation, and this is modeled as the single degree of freedom system. That is the one of the most simple case that we considered, and we all know that the hammer foundations, they are subjected to pulse type of loading which can be of different shapes such as square, rectangular, half sign, etc. So, here in this case we took a rectangular pulse which is shown by this particular figure. So, we can see that here Tp is the duration of this pulse and the magnitude of the pulse is represented by Fr. Now, coming to the modeling and analysis part, first of all let us see that how we model the pulse loadings. So, I mentioned to you that as far as the hammer foundation under its operating condition is concerned, we will have this kind of loading condition on that. Here again I am repeating that I am considering the rectangular pulse. Now, because of the blast, the another type of the pulse loading which will be occurring, and this is modeled as given in this particular figure, where you can see that from the time 0 up to this time Ta, which we call as the time of arrival of this particular pulse loading. And then because of the blast, it will have positive as well as the negative phase, which is modeled using Friedlander equation, which is given by this equation which is there on this slide. So, here let us understand that what all are these terms. So, we have this from this to this, we have this positive phase duration which is given by this T naught. Then we have negative phase duration which is given by T naught minus. So, this is how the pulse loading, two different types of pulse loadings, they are being modeled. Now, the next logical step is going to be that how are we going to analyze that single degree of freedom which is acted upon by these two different types of pulse loading. Should we go for superposition, or should we consider the simultaneous effect of these two types of pulse loading? Now, as far as such kind of events are concerned, the response is no more be linear, and therefore, principle of superposition is not going to give us the correct picture. So, what we are going to do is we are going to consider the two types of pulse loading acting simultaneously on the single degree of freedom system, which is representing the soil foundation system. Now, based upon the arrival time of this blast loading, we defined 4 cases for the analysis. So, which I am going to show you now here in this slide. There are 2 cases. So, you can see that in the case 1, the pulse loading, that is the rectangular pulse loading, is getting over at the time Tp, and after that only the blast is reaching, or the pulse which is represented by the exponential distribution is reaching the foundation. So, in between this Tp to Ta time, the foundation is going to vibrate freely, but the case can be that the pulse loading is continuous till the positive phase duration of the exponential pulse loading. So, in that case, mathematically it will look like that here this Fr is applicable up to Tp, but from Ta to Tp, that means from this or during this time interval, both the loadings are going to occur. That means Fr as well as this exponential loading. Now, the third case can be that the rectangular pulse is getting over in the negative phase of the exponential pulse loading, and the fourth case was defined that the pulse loading, which is the exponential loading because of the blast event, is getting over before the rectangular pulse. So, what we did, we tried to analyze these 4 cases separately. We tried to develop the governing differential equation for these 4 cases, and then we could solve these differential equation in the closed form manner. So, I will just share with you one case, and accordingly all the other cases were formalized and analyzed. So, here I am just showing you the first case. So, the governing differential equations or the equations of motion, they are written in these particular form for different time durations. So, once we have these governing differential equations, then we have to solve these with the help of the initial conditions. Now, take a note that at time t equal to 0, I will be taking the initial conditions as the displacement and the velocity of the system is going to be equal to 0. But wherever there is a change in the equation system, here in different time duration, there the initial condition for the second time duration will be the last condition which was there for the first time duration. That means the condition at time t equal to Tp will be the initial condition for this particular equation, and so on. So then we solved it using the first principle, and we could get the closed form analytical solution for these equations. Similarly, I am not going into the mathematical details of the other cases, but in the similar manner we generated the governing differential equations for case 2, 3 and 4, and then solved it with the help of appropriate initial conditions. So, coming to the results and discussion, first we will see that how some of these specific solutions were carried out and how the result matched with the one which we have already in the literature. So, we took one study which was conducted by Chehab and Elnagar. In this study, what they did was that the foundation system was subjected to different types of the pulse loading, and they used the Laplace transformation to get the time displacement history for that. So, what we did in our case, we made the loading because of the exponential pulse to be equal to 0, and then we got the results for the rectangular pulse only, and you can see that a perfect match is observed between both the results. Similar simulation was carried out for another study which is mentioned here. What they did is that they took this blast loading, that is the exponential pulse with the negative phase, and then they tried to analyze the situation with the help of a numerical approach, and they used the software Mathematica. However, what we have done is we got the analytical solution. So, when we compared a particular case of our study with their study, and then this is what is the result, and you can see that a good match is observed. So, after carrying out these specific simulations, then we went for the detailed parametric study in order to understand the effect of various input parameters on the response of the soil foundation system, or to say that on the displacement time history of the system. So, one such case is presented here, that is where we are studying the effect of mass of the soil foundation system on displacement time history. And you can see here there are 4 graphs, and these are representing the respective cases for all the 4 cases, that is 1, 2, 3 and 4. I have already explained you that what all these cases correspond to. So, as you can see that with the increase in mass, that is from 150 tonnes to 250 tonnes, throughout the negative as well as the positive displacement is reduced. Although the magnitude is not really legible from these figures, so I kind of tabulated these. So, you can see that different columns are there with respect to the various cases, and as the mass is increasing from 150 to 250 tonnes, the displacement, that is maximum positive as well as maximum negative displacements, they are reducing almost for all the cases. Now then, coming to the study which we conducted to understand the effect of stiffness on displacement time history. Again here the results are presented for all the 4 cases. These cases are defined on the basis of the arrival time of the exponential pulse loading. So, we can see that when the system's stiffness is more, that is I am varying it from 250 kilonewton per millimeter to 1000 kilonewton per millimeter. So, with the increase in the stiffness, we get the lesser value of the displacement, that is as expected. Now, here one thing you can notice that the maximum peak, that is positive as well as the negative peak, for each cases the time instant at which these peaks are occurring may not be same. It will depend upon the kind of interaction that 2 different types of pulse loading are having with each other. So, here the results have been quantified. So, we can see that in almost all the cases, positive as well as the negative maximum displacement is reducing when the stiffness value is increased. So, we took the typical values like from 250 kilonewton per millimeter to 1000 kilonewton per millimeter, and here we tried to quantify, and then you can see how the variation is like from 50% to maximum of about, let us say, 68 or 69% reduction is observed. Then coming to the next parameter, that is the magnitude of rectangular pulse loading. So, here we started with the 0 value up to 15,000 kilonewton, and for all the 4 cases this is how the response is going to look like, and you can see that especially in 4th case how it is significantly different than the other 3 cases, and here we have tabulated all the maximum positive as well as the negative displacement values corresponding to every case. So, here there is no definite trend is observed, although it is expected that when we increase this magnitude of the rectangular pulse loading, it is expected that the displacement is going to increase. But please remember that depending upon the case, the negative phase also comes into picture and it interacts with the magnitude of the rectangular pulse loading, and therefore, you will see that somewhere the trend gets reversed. For example, if you take the negative maximum displacement, so it reduces first and then it increases here. So, there is an increase here in this case. So, it will depend upon how these 2 different types of pulse loadings they are interacting. Then the next parameter that we took was the peak load for the exponential pulse. So, here we started with the 0 magnitude and we went up to 30,000 kilonewton, and this is how the time displacement history is going to look like for all the 4 cases, and this is the results which have been summarized here in the form of a table. So, this is what is your maximum positive displacement for case 1, and this is the maximum negative displacement for case 1. So, here it is a very clear situation that not only the maximum positive displacement, but maximum negative displacement also increases with an increase in this parameter, which is the peak load of the exponential pulse. So, and the same thing is happening in all the 4 cases, and then you can see one observation here that for case 2 and case 3 not much difference is there in the result. This is very obvious because of the fact that in one case the rectangular pulse is getting over in the positive phase of the exponential pulse, and in another case it is getting over in the negative phase of the exponential pulse. And for case 4 you can see that these are the results. Then coming to the effect of damping ratio on the time displacement history, we all know that for an undamped system, that is when the damping ratio is equal to 0, we get the maximum displacement, and as the damping ratio increases, your displacement will keep on reducing, and the same thing is being observed for all the 4 cases. Let us take a look at the quantitative part of this parameter. So, for all the cases, as we increased the damping ratio from 0 to 20%, the displacement reduced significantly, and here the percentage reduction is also given in the last row here. So, you can see that the reduction can be as high as 62.2%, approximately 63%, and in another case, like for the same case and the negative maximum displacement, it is about 38%. So, here in this case the damping ratio is more sensitive towards, or let me put it in this way, that the maximum displacement, which is the positive displacement, is more sensitive towards any change in the damping ratio as compared to maximum negative displacement. Now, it is the one of the most important parameter, that is the wave decay parameter. This is with reference to the exponential pulse loading, and if you recall, when I showed you the expression for that exponential pulse loading, the wave was decaying with a parameter that we denoted as B. So, here what we did is that we tried to vary that particular parameter and then try to see that how it influences the displacement time history of the soil foundation system under consideration. So, the values were varied between 0.25 to 10. All these values were taken from the existing literature, and the details of all these have been given in the paper. So, we can see that the moment you increase the value of this wave decay parameter, the diminishing of this exponential wave is faster, and that is what is reflected in all these results. Again, here you will see that the peak of the maximum negative as well as the positive displacement, it is not necessary that for all the cases of B they will be occurring at the same time instant. Again, it will depend upon how the two different pulse loadings they are interacting with each other, and what is the time of arrival that the exponential pulse is reaching to the soil foundation system and make the system vibrate under the combined effect of rectangular as well as the exponential pulse loading. Now, here we have quantified all the results. So, maximum positive as well as maximum negative displacements are tabulated for all the cases. So, as this wave decay parameter is increasing, say from 0.25 to 10, see how for every case the displacements are reducing. Not only the maximum positive displacement, but also the maximum negative displacements are also reducing. So, this is how we saw that how various input parameters, they influence the response of the soil foundation system under the combined action of two different types of pulse loading, where one pulse loading has positive as well as the negative phase. So, what we summarize as a part of this work and some of the salient concluding marks is that here we analyzed a hammer foundation under the combined effect of rectangular and the exponential pulse loading. A point is to be noted here that this exponential pulse loading has positive as well as the negative phase with it. Then we are not considering the superposition, but we are considering the interaction of these two pulse loadings and then trying to obtain the solution. Then we could quantify the influence of various system parameters such as mass, stiffness, magnitude of the pulse loading, wave decay parameter and the damping ratio, and the details I just discussed with you. So, in the presence of such loadings, foundations may become non-serviceable. You all know that machine foundations, they have very stringent displacement criteria. So, the displacement should always be within the permissible limit, and that limit for such type of foundations, they are very low. So, what we are getting out of this analysis is that just in case if such type of the event occurs, then how the displacements are going to be, and if these displacements are more than the permissible value, then we need to design for the proper vibration mitigation measures. So, basically the outcome of this study is useful in designing the suitable barriers. So, here what I tried to give you the idea that how simply we modeled the hammer foundation, which is acted upon by the rectangular pulse loading, plus in the event of a blast or the nearby mining activity, it can also be subjected to the exponential pulse loading with the negative phase, how we can get the displacement time history with respect to that, and how the outcome is going to be useful for designing the suitable barrier system, which was beyond the scope of this particular work. However, the future work is in progress in order to look into all these aspects. So, thank you very much. I thank the organizers to give me the opportunity to share our work on a platform like our conference.